I know when that hotline bling, that can only mean one thing. You're worried about the next exam, aren't you? That's all right. I'll see what I can do. It's good to be wanted sometimes. But hi. So today we're going to do a little general one, some limiting reagent stuff. And you usually hear about limiting reagents right after your introduction into stoichiometry. And that's because limiting reagents, those calculations are just more stoichiometry stuff. And it won't be the last stoichiometry stuff you run into in the next 2 or 3 chapters, most likely. But the idea behind a limiting reagent is that a lot of times when you're doing a reaction, you're not reacting your reactants in what we call a stoichiometric amount. In other words, you don't have exactly as much of one to react with all of the other, so all your reactants go away. Usually what happens is you do have some left over, which we call the excess reagent. And the reactant that actually gets completely used up in the reaction, we call the limiting reagent, because it limits or controls how much product you can make. Here's an analogy I like to use. It's what I call the great hot dog mystery. So if you want some hot dogs, you go to the grocery store, and I think this is still true. You get a pack of buns and a pack of Franks, or wieners, or dogs, whatever they call them in your neck of the woods. But you know, the hot dog buns come in packs of 10, but the dogs themselves, they come in packs of 8. And therein lies the mystery. Why are they a different number? I mean, you buy one, you're gonna buy the other. Can't the hot dog people and the bread people like figure it out that they should really have the same number in each pack? So for all you young people who just can never understand how grown-ups can, you know, keep disagreeing over what seems to be issues that we should be able to, you know, come to some consensus on, just remember, hot dog people and bread people can't decide between 8 or 10. You know, why are the Palestinians and the Israelis still fighting? Well, the hot dog people and the bread people can't figure out, you know, how much stuff to put in packs. You know, why can't the police and our inner city youth, you know, stop fighting with each other? The hot dog people and the bread people can't decide on a stupid number. Why can't Republicans and Democrats come to some type of agreement over health care or gun control? The hot dog people and the bread people, they can't get their shit together to decide 10 or 8. What hope do we have for anything beyond that? But anyway, limited reagents. No, actually, no. I got to finish my hot dog example. Sometimes I get carried away. But yeah. If you want to make hot dogs, you're only going to be able to make 8 hot dogs because you're limited by the number of Franks in your hot dog pack. You can't make 10 hot dogs because you don't have 10 Franks. So you're going to have 2 excess buns left over. And yeah, I guess you could buy 80 of each, but let's not get carried away, folks. Every analogy has its limits. But in chemistry, like I said, a lot of times you'll have some excess amount left over. And a lot of times that is intentional. You know, sometimes chemists work with really expensive reagents or reactants. Reagent's another word for reactant, remember. Really expensive chemicals. And if you want to do reactions, do chemistry with those chemicals, pick a word, right? Then you want to make sure that it all gets used up for the thing you want it to do. You will use a cheaper reagent. If you're reacting with a much cheaper reagent, you're going to use an excess amount of the cheaper stuff to make sure all the more expensive stuff gets used for its intended purpose. And sometimes it is a bit of laziness. You know, it's like, okay, I'm going to react 2 grams with this. 4 grams with this ought to be enough. And then you worry about the yields later. So let's look at an example, a chemistry example, no more food examples. And we're going to use an example from my book, Cheap Plug. This is Try It Yourself problem P15 on page 128. So we have this reaction between uranium and fluorine to give you uranium 6 fluoride. And for part A, you're told that you start with 15 moles of each reactant, and you're asked which is the limiting reagent. And then you're asked how many moles of product can you get. All right, so we can't answer the second question until we know which one is the limiting reagent, because that'll be the one that determines our theoretical yield. So there's a few different ways to do a limiting reagent problem. Usually they involve at least a couple of calculations. But the way I like to do it is just to start with, pick one and see how much the other you need to determine which one is the limiting reagent. So let's say all 15 moles of uranium react. I just usually pick whichever one's written first. All right. How many moles of fluorine do you need to react with all 15 moles of uranium? So it's a stoichiometry problem, just a simple mole-to-mole conversion. So remember, whenever you want to convert moles of one thing to moles of something else, you look at our given reaction, and it looks like a 1-to-3 ratio. 3 moles of F2 for every 1 mole of U. So that would give us 45 moles of fluorine that we would need to react with all of our uranium. But if you compare how much we need with how much we're given, or we start with, we only have 15 moles. So we don't have enough fluorine to react with all the uranium, just like we didn't have enough franks to combine with all of our buns. So if you look at how much you need with how much you have, you don't have enough fluorine, so it looks like fluorine will be your limiting reagent. And like I said, I usually just pick whichever one's written first, but you can pick either one and come to the same answer. All right, we also have 15 moles of fluorine to start with. How many moles of uranium do you need? So if you go in that direction, it's still 1-to-3. Except now, the 3 is on the bottom. Oops. Because you want to get rid of fluorine this time. That gives you 5 moles. So we need 5 moles. We have 15. So we have more than enough. In fact, you could say we have an excess amount. So we only have 2 reactants, which is pretty common in this class. If one of them is in excess, the other one must be limiting. It's an ugly arrow. There we go. That's not much better. Hey, I get obsessive sometimes. So no. So that means that fluorine is still our limiting reagent. So you don't have to do both, but no matter which one you do, you come to the same conclusion. Fluorine will be your limiting reagent. And now that we know what our limiting reagent is, now we can figure out our theoretical yield of our product. So again, it's another mole-to-mole conversion. So you have 15 moles of fluorine. We know all of it's going to react. And according to our reaction, it's going to be 1 mole of UF6 for every 3 moles of fluorine. So that means we should get 5 moles of product from this reaction. All right, so let's look at another example, and this time we'll do a gram to gram type of problem like we did previously when we introduced stoichiometry. So same reaction, only now we'll start with 15 grams of each reactant. And again, we'll figure out what the limiting reagent is, and we'll use that to figure out how much product we're going to get. So again, same as before, pick one, see how much of the other you need. So if all 15 grams react, how many grams of fluorine do you need? So this time we have to convert grams to moles. And remember, anytime you want to convert grams to moles, you use molar mass. So now we're in the same place we were before. And now we can go moles of what's given to moles of what we're looking for. And it's the same reaction, so it's still 3 to 1. Now, remember, grams to moles is molar mass. The mole to mole, we're just looking at the coefficients. And so we can compare grams to grams. We can use fluorine's molar mass of 38 grams per mole. Oops, do that. To give us units of grams of fluorine, which is like 7.18 grams of fluorine that we need. So again, you compare how much you're given or how much you need. We need about 7 grams. We have 15. So again, we have an excess. So if one is excess, then the other must be limiting. So uranium must be our limiting reagent. So now that we know what the limiting reagent is, we can figure out our theoretical yield of product. So we start with that 15 grams of uranium. Convert grams to moles. And again, we look at our chemical equation and see that we're going to get 1 mole of product for every 1 mole of uranium. And converting moles to grams, we use UF6's molar mass, which is 352 grams per mole. It's ugly 6. There we go. And that gives us an answer of 22.2 grams of uranium 6 fluoride. So, like I said, there's a couple of different ways you can do these types of problems. Another one that's really popular is just to start with both amounts and convert both to products. That works too. Whichever one is lower, that's the winner. You might see other videos do that. Although, if you're only looking for the limiting reagent, you're kind of doing twice as much work as you need to. If you're looking for the theoretical yield, then yeah, same work either way. But I like like I said, one reason I like this is because it's just more stoichiometry. So it's just an extension of what you were taught a little bit earlier in the chapter. And at this point, just remember, stoichiometry is still the same unit conversion stuff that you were taught probably in the very first chapter. And at this point, we're only really doing 2 conversions, you've noticed. We're doing those mole to mole conversions based on the equation and gram to mole conversions based on our using molar mass. There's a third one that we were taught earlier in the chapter using Avogadro's number, but we really don't use that one too much as we get into chemical reactions. We don't do a lot on the atomic scale in Gen Chem. We usually just stick on the mole scale. So probably since you started looking at reactions in stoichiometry, you've been doing a lot of calculations, but go back and notice it's only the same 2 conversions, kind of like today. Our gram to mole, mole to mole. So once you kind of get that, then that'll help a lot, because when we go into the next chapter and start talking about solutions, we're going to introduce another conversion factor with molarity and a couple more later on. But it's still just the same 4 or 5 conversions that we're kind of doing in different little ways. So same stuff, different problem. All right, so that'll be it for today. I notice I say all right a lot, or okay, in these videos, which I did back in my old Gen Chem Concepts channel, the one I still have somewhere else on YouTube, you know, me and the notepad. I used to do that early on, and now I'm doing it again with these. It's just, I'll pause for a minute and go, okay. I'm like, McAfee, is that his name from South Park? Yeah, Mr. McAfee, yeah. Anyway, I should have stopped 5 minutes ago. So, bye.
What a prick.